Hello and welcome to this lecture 7 of applied ergonomics. We were talking about the different flow charts and we had also mentioned about some practical examples related to the outline, the process outline chart, the materials flow chart and also the 200 system, the 200 chart that we described. The other kind of representation is a flow diagram, which again can be found out in this particular slide here. The purpose of a flow diagram is, like, in the simplest manner you could record anything as the way that material again is flowing from stores in terms of various things like transportation of the materials and probably operations, and if some inspection is involved. So in this case, for example, a material flows from a permanent storage, okay, all the way to let us say station A, which does certain operation A, certain operation 1, beyond which the material again flows from 1 to station 2, and so there is a transportation of material between station 1 and station A and station B. So the operation B is being performed in station 2, and similarly the material flows again between 2 and 3, where the material C, an operation C, is being done on the particular workpiece. So you are representing this in terms of transportation and operations, okay. And then again it is operated where it goes to an inspection station 1, where inspection activity D is carried out, followed by let us say transportation to again another area which is where the output would go from, and so typically it has to wait up till the carriage comes and takes this material from this station to the next probably process, okay. So there is an output and there is a temporary delay of the material waiting before it is picked up, so that you can have another set of material flow back. So this is a very simple view of the whole work plan, okay, to a certain scale, and you can link the diagram indicating the path followed by the object under study to give an idea of how much length scales are being translated, okay, between the storage or let us say the operations or the different inspection steps which are there. So it gives an overall view of an existing or proposed process and can be used for making improvements to the process. Supposing there is too much of crisscross, this you are seeing already is a crisscross between the material going from section C to the inspection and the store to A. So can I develop some paths where there are not many delays because of the crisscross? Let us say if I had an AGV system here, automated guided vehicle, obviously there we will have to schedule that the crisscross may not happen at the same point of time, so that there are two vehicles colliding into each other. So that kind of a case should not be happening. So it is a very important layout requirement that there should not be any hindrance to the flow, and based on that you take certain decisions and also change certain layouts. So it shows that sort of the path followed by material, man and equipment is done in a very uniform manner. So try to do as much as parallelity or parallelism into planning such layouts. That is the whole idea. So this is a flow diagram. So we also have various other representations for recording the data. For example, this is a man machine chart which talks about how an operator can be mapped in terms of his setup and let us say working and idle times with respect to a machine. For example, let us say look at this one operator, one machine system. So this is the machine, a time scale is associated on the y axis, and this is the operator. So you can see that when the operator is setting up the machine is being set up, okay. So the machine is idle at that time when it is being set up. The moment the setup is completed, the operator becomes idle as the machine starts running, okay. So this is an important problem which has to be solved, that how to reduce some of these idle time. So best idea would be that if I give one worker two machines to operate on. Now you see here in this case you have two different setups for the machine 1 and machine 2, which has to be executed by the same worker. So the machine 1 is being set up for the first time between 0 and 0.5 seconds by the worker, and the moment this is set up, the running can start of that particular machine after 0.5 seconds, and now the worker does not remain idle, because he has to set up another time or another machine which can be set up too, okay. And so that you can make the so as you are doing it, machine 1 is already running and machine 2 is being set up, and now you can see that the machine 2 starts running here, okay. And there is a small amount of time overlapping between these two machines where the operator is still idle. So, can I actually now load 3 machines on the same operator. So, this way I can keep on utilizing the operator's time and engage him between multiple machines, so that we do not have any question of overlap time wise between 2 machines. That means setup being done together, that is avoided, and you can also give a time by time very nice sequence for the operator, so that all the 3-4 different machines which engages him completely are worked in parallel at different start points. Okay, so in this case, for example, 3 machine 1 operator system, you see that setup 1, setup 2 and setup 3 indicates the setup times for 3 machines. So, the operator now is between 0 and 0.5 seconds setting up the first machine, between this can be seen here, between 0.5 and 1 second setting up the second machine, and between, let us say, 1 and 1 second setting up the third machine, and so he is never idle. And if you look at how the machine is being run, so after that this starts running and there is some idle time, okay. Then again when the second machine is set up, this starts running, it goes all the way from here to this point, this point, and there is some idle time, and similarly when the third machine is being set up, it will start the running and then it will have some idle time. So, this even idle time can be avoided by packing more machines in a manner, so that you have very less slack between the machine wait time and the operator wait time. So, there is a very nice representation on one particular board to illustrate how much of idle times are there, scales are there on the machines, how much of idle times are there on the operators. So, it is a study which is undertaken to find what number of machines each worker can operate and how many workers can work on each machines, and it enables the management to sort of minimize the idle time of worker and also that of machines, and you can use the machines in full capacity by looking at the man machine chart. So, these are nothing but organized intelligent representations carried out in a manner, so that you have less idle times and less slack as far as possible in a work system. Okay. So, we will now start again detailing some of the time studies. So, I think I had mentioned about time studies, that whenever such works and tasks are identified and a process sequence is being developed, you associate some time scales with respect to the independent work and independent tasks which are there in such work systems, and then the time scales can actually add up together to complete the whole operation, and we can call this the addition of such time scales of the whole operation as one cycle time. So, the period required to complete one cycle of an operation, okay, a complete operation which is being split up now into several tasks. Tasks could be material flow, delays, tasks could be related to, let us say, machining. You saw some of the examples earlier. Okay. So, to complete the whole function or the job or the task from start to finish is what a cycle time really would be. And so, a cycle time is a very critical issue, particularly when you have multiple work centers working together in a certain sequence, okay, for the task to be carried out. And one such illustration is assembly lines, where there are multiple work centers, multiple staff working together, and somehow the behavior of each staff with respect to the other matters overall in the whole productivity or the speed at which the overall assembly line can be operated. So, we will do some problem examples as well to sort of get a feel of what exactly I am talking about time study and how we can do it. So, we will just first look into some techniques of how time studies can be carried out. So, the first technique, I think CMO chart I had already introduced earlier, where we talked about simultaneous motion and we talked about assigning time scales of simultaneous to such simultaneous motions. The other very important time study technique which was introduced by Gilbreth was by looking at a little source of light bulb, maybe a small LED in the current days, which is attached to the hand or finger of any operator, okay, or maybe any other body part which is involved in the motion sequence associated with the task to be executed, okay, and this particular motion is being trapped and in terms of continuously taken photographs. So, basically you see this is a small source of light, and this light is actually going through this path as the operator executes the whole task, and so you can actually get a very good idea about the time scales associated with such a task as the motion completes from one such snapshot to the other snapshot. So, you can have a continuous streak of light this way when you film this at a certain speed, okay, so that you define more or less the work zone based on such speeds, and because you are recording at a certain rate, obviously the time scales automatically come out. So, exact start point and exact end points can be precisely found out for a certain task, okay, in this particular manner. And with this information of the framing rate as well as the beginning of the streak and the end of the streak, one could suitably get very accurate values of time scales associated with different motion sequences. A similar idea comes through this chronocycle graph, which is a special type of cycle graph. Here the light source is suitably interrupted electrically, so that the path of motion in the photograph appears as a series of pear shaped spots. Basically you can get an idea of directions, okay, in this particular thing. So, you are when you are imaging or you are introducing an imaging modality, you can change the let us say the acquisition screen size in a manner, so that you get a larger perspective or a larger area in one case, and as the window changes the spot of light also becomes smaller and smaller. So, in this way you can play around with the imaging modalities, so that you have a highest spot size at some time, and then maybe keep on changing the variation, or keep on changing with time the spot size, so that you have a pear shape. And so, the whole motion direction could be sort of split up into such pear shapes or arrows, okay. So, these are some arrows, for example. So, these arrows are indicating the motion direction, okay. So, the why pear shape, why we do this image control is just because we want to find out what is the direction. So, the direction is typically from the broad end, where the window of light was quite bigger, or light acquisition, to the smaller end, where the window of the light acquisition was smaller. So, we try to find out what is exactly the direction at a certain point of time associated with a certain task or a certain process. So, the pointed end of the pear shows the direction of movement, and more elongated and spaced pear spots indicate higher speeds of operation, and so it can help in studying complex and restricted motions also, which otherwise may be little difficult. That exactly, let us say it is in a corner, the motion is along the corner, and it is very difficult to otherwise find out what is the start and stop of such a motion. So, you could actually do this, use this image analysis technique for intelligently finding out where exactly the hand is proceeding at what point of time, which can be considered as the task in totality. So, how time studies are carried out? So, typically you establish a standard job method first. You have been doing that using so many cycle charts, so many different forms of representation, outline charts, etc., which you did in the first module of the last lecture. Then you break down the jobs into elements, study the jobs properly, rate the workers' performance. This is a very important aspect of time study, that a person may be very highly skilled to deliver at a faster rate, or a person may be less skilled to deliver at a slower rate. So, you should have some kind of a rating based on if a performance of a person is high or low. You could actually associate varied time scales and keep a slack in a system which kind of accommodates that aspect, okay, from variation from person to person, so that your time study could be more generic, more generically applied, more accurate, so on and so forth. And then you compute average time scales and compute the normal time, which is actually it's the you can say the elemental time. Element is one element of a certain task, okay, times the rating factor. So, here is where you are trying to give some heed to the worker's performance. So, if I rate at a particular worker at 1.1, that means he is doing 110%, the actual rating that an average worker would do. So, this rating factor actually becomes important in terms of the individual performances. And then you have a standard time, which is actually related to what this normal time is, okay, and introducing the normal time and then an allowance factor. And this allowance factor is typically made because there is always a certain degree of slack that the management wishes for smooth flow associated with the system. It is not that you can keep it at zero slack. There is some allowance in between which is kept in terms of times, because there may be issues related to different non-compliance factors which may couple in such a work system. For example, the material which comes may be damaged on a particular case. where there may be certain change, the material that you have picked up for assembly, you realize it's not good, you throw it and take another one, another sample. So there's some slack which is always needed for a smooth flow of any system. And so therefore standard time is set in accordance with that normal cycle time and with an allowance factor which you provide. So let's do a small example. So we have a particular time study to be done of a job where we have split up into different elements. So the whole job is divided into 4 different tasks or 4 different elements, and each of these elements have different time scales associated with it. For example, task 1 takes about 0.251 seconds, 2 takes about 0.529 seconds, so on and so forth. There is a rating factor associated with each of these because they have been done by 4 different operators, who one of them operates at 110% efficiency, another is a little bit lower at 105% efficiency, so on and so forth. And then you have again the requirement is to calculate what is the overall standard time of this particular job, and you'll have to use an allowance factor of 20%. Okay, so you do whatever time scales you generate, normal times of the whole process, including all these 4 elements coupled together. You have to multiply, or you have to do it at 120% to calculate what is going to be the actual time scale. So let's do it. So we use just the simple formulation here. Normal time equals the elemental average time times the rating factor. Okay. Now, how we have arrived at the elemental average time is based on some of the techniques that I have earlier illustrated, maybe do video filming or microfilming and add some time scales. I would just like to mention that in the CMO chart example, we had also talked about time units. So there the time units about 1/2000th of a minute. So it's a very, very small time unit, and so therefore essentially we are filming all the micro motions which are associated with such time scales or time units. And I would like to sort of say here that when you do time studies, or when you do, let us say motion studies, etc., there is always how small or what is the resolution at which you can do this, at what is the minimum level in which you can record, so that you get the more precision or more accuracy, okay, in the whole process. So you have normal time which is associated with the elemental average time and rating factor. So I do this for all the elements. For example, if I looked at element 1, for example, you have a total elemental average time given as 0.251 time units, let us say minutes, and I have a rating factor for this particular operator who is delivering the element 1 as about 100, he does it at 110%, so the rating factor is 1.10. So I will have the normal time estimated in this particular case as the elemental time, average time, times the rating factor. This becomes equal to 0.2761. Similarly, you could do it for multiple elements. I am going to make a table here which talks about different elements. Okay, so you have elements here listed as 1, 2, 3, 4. So there are 4 different elements listed here. Okay, and there are different time scales and rating factors we are associated. So the elemental average times are written down as 0.251. Let us say these are minutes. Okay, then you have 0.591, 0.421, and similarly 0.357. These are found out, or these are being reported in this particular table, which has measured the average time scales associated with these 4 tasks. The rating factor is assigned, so the RF is assigned to be 110% for the operator working on the first task element. Okay, and let us say 1.15 here, 1.10 here, and 1.05 here. Okay, so now there can be 2 issues. One is that we can look into each element of a certain task being done by a single operator and say how efficiently is delivering element 1, how efficiently is delivering element 2, etc. The other issue could be related to 2 different tasks which are planned together for a greater cause or a greater, let us say, task assembly or a job. So, it all depends on how you infer on a particular situation. So, supposing if I had a case where on a machine shop, for example, let us say a CNC or NC system, there is an operator who actually inspects a cylinder block using a pressure gauge, and then he also loads this in a NC machine, center 1, and from center 1 it goes to center 2 to center 3, so on and so forth. So, in that event, the efficiency of checking the particular engine block using a pressure gauge of different, let us say, times during the whole shift of operation may be different by the worker. For example, if this is a very heavy task where there is, let us say, such a gauge which is balanced through a spring balancer overhead, and you are pulling this gauge and putting it into a certain block and doing it for 3 blocks or certain cylinder, doing it for 3 or 4 cylinders in a single block, it is a very heavy task. So, probably loading the block into the machine may not be that heavy in comparison to this inspection that you are carrying out, and so therefore, your efficiency may die down towards the end of the shift where you have already been exercising this for multiple times. For example, some machine shop or some such CNC line makes about 300 blocks in a particular shift of 8 hours. So, an operator towards the beginning may have slightly greater efficiency on the heavier tasks, and towards the end may have a lowering down of the efficiency more for the heavier task in comparison to the lighter task. So, you could work out the details in such a context. On the other hand, it could also be a case where you are having, let us say, multiple tasks given a certain process sequence, okay, which is about, let us say, the car making process between weld and paint and assembly. So, there you are doing a task study. So, you basically concerned more with one individual operator, one individual station as one task. So, it is upon you how you are basically trying to introduce the concept of the work study. So, whatever it is, so this RF can vary between a single operator, as you saw in case 1, the example 1, or between multiple operators where multiple stakeholders are involved for a process, or different tasks are done by multiple operators for a process from a case to case basis. So, here the total normal times which are involved here, for example, are just a product between the elemental average time and the rating factor. So, we give this as 0.2761, 0.6084, 0.4631 and 0.3749. So, a total amount of time which is spent here, or the total normal time which is spent here is about close to 1.73 minutes. It is a summation of all NTs, T varying between 1 to 4, and here we can calculate that because there is a 20% allowance factor. So, the standard time for this particular operation will come out to be the normal times times of 1 plus the allowance factor. So, in this case normal time is 1.73 minutes. So, you have just multiplied that by 1.2, allowance factor is 20%, okay. So, 0.2, and so the standard time you can say for this particular operation is about 2.08 minutes, okay. So, that is how you record the standard times for different operations. So, an operation which is comprised of 4 different task elements which are having individual components of their normal times based on the operator efficiency, the average operator efficiency is mapped in terms of the standard time which I will assign finally to this particular set of 4 elements constituting one particular job, okay. So, that is how we do the time study. So, I think I will close on here this particular module, and the next module we will see how different time scales associated with different operators may sometimes balance or disbalance an assembly line and may play its role in terms of increase decrease productivity. So, as of now, thank you very much.